The plans for the next 4 days, we're going to cover a variety of topics that relate to trying to get applications to run on AMD GPUs. The schedule for today is we're going to go over the AMD architecture. We'll have an introduction to the HIP programming language, and then we will talk about HIPifying or porting applications to the HIP language. Day 2, we're going to cover a variety of higher level languages, starting with OpenMP and then COCOS or other performance portable languages. Day 3, we're going to get deeper into the architecture and how to get performance on AMD on the AMD system. And so that will include the memory model for the AMD nodes, GPU-aware MPI, Affinity. And then day 4, we'll go over the tools, which include RockProf, OmniTrace, OmniPerf, and the ROCm GDB debugger. So plan your schedule accordingly. The slides from these presentations are on Lumi at project, and the project number under slides. And there's a HackMD site that has a markdown document to help with the exercises. The exercises are kind of short. We don't allocate a lot of time for them, so you can do them as you have. You can start them during the exercise sessions and then do the ones that you find are most appropriate. I think we hear somebody. Okay. Okay, so if you have, I'm going to go ahead to the next set of slides.
Bob, I'm here now. I can have audio if you want me.
Sure.
Up to you.
So I already went over the presentation roadmap.
Yeah. Do you want to continue or continue?
No, you can go ahead and take over.
Okay, 1 moment. Find the server. Okay. Is it okay? Okay. So my name is George Markomanolos. I work in the same team with Bob in HPC Software Solutions. And one of our tasks is about the training, as we do here now. Now now in this short presentation, we'll talk about the Lumi for the exercises. You should have all got an invitation for a project, I hope at least. Problems, contact support, the user support. There's a website, you can submit a form. Documentation for Lumi is here, docs.lumi supercomputer. These slides are already in the project/slides. So if you are belong to this group, you can run the command groups, and you will see that you are in this project, just to be sure. Also, Lumi has recently been upgraded to the Lumi 22.08 software stack, which involve also some ROCm versus newer and GC. Now, file spaces will not do something extreme here, but there's quota, right? So we can it's easily to kill the quota because it depends on the number of the files also. If you create a lot of files, we can have problem to write in the project. But our file spaces is projects underscore. This is mainly for more generic stuff, and for your more working directory, you'll be in Scratch, project, and user ID. this is your username basically. So I suppose everybody knows the username. Any question? Okay. So how do we log into Lumi? I hope that everybody has already access. It's SSH username at lumi.csc.fi. To simplify the login to Lumi, you can add the following to your .ssh config file. Basically, these are instructions for if you have Linux environment. There are also for Windows, but I don't have at least here something for Windows. You can edit this file here and add something like that. Host Lumi user is your real username, not the, I don't know. For me, it's gmarkoman, host name, and which SSH key to use, so to identify which file to use, because on Lumi we log in with without password but through the SSH files, but they demand to have a passphrase, theoretically at least. So if you cannot log in and you don't have passphrase, maybe you need to create an SSH key with passphrase. I suppose both work, but I'm not sure without passphrase. And just to keep the server, the connection more active, alive, you can define these things. The server alive lines may add it to avoid times out when idle, so it helps. And so now you can log in with SSH username at Lumi. Basically, even that's SSH Lumi, you will be able to connect. So I will stay here a bit just to be sure that does everybody has connected on Lumi?
Hi, George. Actually, I did not receive any credential by email. I'm Antonio Memolo from Cineca.
Okay. So someone from the organizers, because I was not the one who did that. You registered normally, right, for the training?
I registered.
Yeah, I see someone in the chat, neither myself. One moment, because I cannot see the chat. Bob, can you contact to organizers to see why these people have no credentials yet?
You mean my email?
No, I'm talking to Bob. Bob is my colleague from AMD.
Right.
Okay,
So
sorry,
we
sorry,
should
sorry.
check with.
To talk with organizers, because we're not the ones who set up the accounts. The organizers did. So to talk to organizers to ask why anybody else. So it's two people. I don't see the chat. How many people are they that they don't have accounts?
So we have Antonio and Guillaume that did not get credentials for Lumi access.
Can you hear me?
Check your.
Yes.
Oh, okay. So my problem is that I registered correctly, I think, in Puhuri. I already have a Lumia access, but I don't have access to the actual project. Usually I access to the my CSC, and then from my CSC I have access to
Oh yeah.
what is the other service?
So
So my access ID. So they are already linked, but anyway, in Lumia I don't have access to that project. So that is my problem.
so they are linked.
Yes, they are linked.
Because that's the trick for me to see the account, just to link, and then it works for all the future accounts.
Yeah, usually it worked in the past. But with a groups command, for example, I don't see the actual project for this workshop.
So can you go with can you send a ticket to the user support? Because this is more a user support.
Okay.
I have here in the laser point. I think that's a user support for accounts or something, and say that this kind
All
of
right.
urgent as
Yes.
the training is just happening. Now for the other two accounts, I suppose Bob started talking with organizers. I don't know why you didn't get credentials.
Can you hear me?
Yes.
Yeah, so I have the same situation as Filippo. So I already have a CSE account I linked it. It's linked. I'm already in conversation with the user support, but I still don't have access to the project. So
And they cannot solve it?
I don't know. I haven't received any reply. I think I had also kept Miriam in CC. So
Okay. So what we can do probably is to try to give you some files, to your normal account, something like that. If you don't have access to the project, at least you have access to Lumi.
yeah, that would be
I
fine.
see. So there is a chat, but I don't see the chat here. Okay.
So I'll send a note to Miriam to check on whether the invite got sent, and if you're having trouble with the accounts, it's a little bit confusing how to set up accounts on Lumi. So checking with the support is the best way to resolve that issue, and it may take a little bit of time.
I think the most confusing is linking the CSC account to the other one. But once you do that, I remember, I have done like 4 or 5 different projects, and I could get access immediately almost. That's why it's a bit confusing.
Yeah,
Okay.
sometimes you don't show up in groups for a little bit, but it's.
Yeah, I was thinking too that maybe there's some synchronization problem because maybe there's some synchronization between the two services. Maybe I'm not sure.
Some things are manual, I think, still. But okay, but if you set the support can talk to the people who have the scripts and say, please run the script, for example.
Okay, we have a question what the project number is, and I think that's on the other
Sorry.
slide.
Yeah, this one. 465300380. So for workshop, you need to declare, okay, you want to do a log, for example, you have to define the project, which the project is this one, and use a small GQ in the SLAM, maybe because it's more easy to access. It will not do so large allocations. Suppose a sub allocation. I'm also, this is not, with the shared jobs, I don't see the shared jobs on Lumi. So I think it's exclusive by default. Use data CPUs to get the GPUs that you need, and ask for the number of CPUs needed. And if you experience problems, temporary directory conflicts, you can redirect your temporary files to another directory. I hope you don't need this for Lumi. You have situations for other systems, but I think on Lumi is exclusive by default. And try to work here or in your own projects, and on your own, on your own project if you don't have access here, and we can share the files. It will not be a problem. Now, for people who, so you can clone this in your project, and for people who have access to this project, I have it already here. So exercise / HPC training examples, and better take it from there because I have fixed something, and I can share it with the people who don't have access. So for the people who have access to the project, do a cp-r, all this directory, but it's not for now. It's basically have later the exercise / HPC training examples. While the people who don't have access to the project, they can clone this, and get the examples. So this is later. This is not yet. I will install them later for this project. And again, the slides is here. The slides for the first presentation of today is already here. Okay. So okay. So this is the last one slide. If you want me to keep it a bit active, the slide to to see the project ID or something, tell me before I continue to the next one.
Maybe you can share the slide with everyone.
Yeah, you mean here probably in the chat, because the slides are here. The slides are here already, but I can try in the chat. Let me see. Okay, let me stop sharing. One moment.
Actually, so I have a question. I'm new to the Lumi supercomputer, and I need information how to connect and do it step by step. Where can I find this kind of information, please?
Okay, one moment to send. There's one. Give me one moment to find it.
So there's a user guide that does help. If you want to chat with me privately, I can walk you through the process.
Oh, can I send file here?
Yes, it would be good, but how can we chat? I don't know. Or I can send you some, I don't know, Skype account or.
So you can go to the chat and just instead of sending to everyone, just pick Bob Robey.
Okay, that's good. I see you. Thank you.
I just say, can you send the file from here or I'm wrong? How to send file in the chat or something? I don't think I can.
You can't put it in the chat.
Sorry?
You can't put the file in the chat.
Yeah,
Okay.
it doesn't allow. Oh.
Maybe you can upload it on the GitHub where the training materials are, if they're not too big.
So if you can't get it from the projects directory, just send me a note in the chat with your email and I will forward you those presentations.
Okay, I get it. Yeah.
So you'll do it?
I will forward anybody
Okay.
who sends me a note in the chat. I will forward.
So before we go to more software, we're going to discuss a bit the architecture of this GPU. Right? It's based on the CDNA2 architecture, and basically, what you can see here on the left is one, let's say, physical MI250X. Okay, and there is a nice white paper that someone can read with many information, and basically you can see like two sockets, but basically it's a dual graphics compute die. Each one's called GCD, and it's quite independent. You can use only the one or both of them. There is 8 stacks of HBM2E. This is a fast memory. Okay, and this is the GPU that's on Lumi, Datel, Cines, Frontier, etc. Now it's constituted by 58 billion transistors, it's 6 nanometers. It has 220 compute units. Although it's not correct to say that, for people who are not familiar, let's say 220 really simple cores, not correlated CPU cores, but to CPU cores, something like that. It's not accurate description, but to help people who are not so familiar. We have 880 second generation matrix cores. This is for matrix operations that various libraries use them, utilize them, and achieve much higher performance, as we will see. And you have 128 gigabyte of HBM2E memory at 3.2 terabytes per second. This is the peak bandwidth, okay? So just to mention something, as you see, you have 2 GCDs, which means the 220 compute units is 110, 110. So if you run one MPI process to this GPU, it will utilize one GCD only, which means it can use up to 110 compute units. And actually, you cannot achieve 3.2 terabytes because it's like 1.6 terabyte per GCD. So without any special framework, technique, etc. With one API process, utilize, let's say, half the GPU. Now, on Slarm is the scheduler. Scheduler is how we submit jobs on Lumi. In general, on supercomputers, but Slarm is the name of the scheduler for Lumi. One GPU, one physical GPU is seen as two GPUs, 1 and 2. So on each node, we have 4 of them, but Slarm will tell us we have 8 GPUs because it recognizes each one as one independent GPU. Okay, so don't be confused when you see 8 GPUs on the node because it's basically 8 GCDs, 1 and 1 times 4. And this is how I have on Slarm 8. Now here, what is that? If I go back and I zoom here, okay, I zoom to one of them, and I start seeing more details, more hardware details, let's say. Again, we said that about 6 nanometers, up to 110 compute units per graphics core die. So 110 compute units, let's say it's of these ones. We have 4 matrix cores per compute unit, and they're enhanced for HPC. Now, if you don't understand this, it's not really important because then you don't utilize it for your code. And if you remember in NVIDIA, the tensor cores, now we have called them matrix cores, and now they support 64-bit operations. So that's why we say enhanced for HPC. They have 8 Infinity Fabric links per die, Infinity Fabric links here and here, and special FP32 operations for double throughput that we will discuss later. Now, this MI250X has the matrix cores have double performance than FP64. So when you use matrix cores with special libraries, for example, theoretically you can achieve double speed than using just the classic FP64 operations. For FP32, we have packed math that we'll explain later that doubles the throughput. So if you continue, you see here the links, and let me go again back. These links are basically here. Okay, how we connect two GCDs. Two GCDs are connected with 4 links, 16 lanes each, running 200 gigabytes per second per direction. One like that, one like that. That's why we say 400 gigabytes per second bidirectional bandwidth. Okay. There are also HDMI links to connect to N4 CPU for coherency and through PCI. And each GCD has 8 of these links, 4 internal, and I used to connect this GCD 0 to GCD 1. Okay, if I can name it 0 and 1, for example. And each OEM has totally 6 times 16. OEM is both of them, okay, combined. And as you see, they have quite significant high performance interconnection. Now, we mentioned here the MI100 because some people have used MI100 before, especially early Lumi users had access to MI100 and later they got access to MI250. Here is the matrix cores. So before there was no FP64 for matrix, support for matrix core. On MI250X there is. Now, our base arithmetic rate for FP64 is 128 flops per compute unit per clock, and while it was 64 for MI100, so we double it. And you see here for different arithmetics, different data types, you have different operations per clock per compute unit. Now, what you see here is for FP64 and FP32, you have same performance. So actually, if you don't do anything special, running FP32, you can get performance like 64 and the opposite, okay? And we'll discuss a bit how you can get better performance. So for matrix cores, The current support of using MFM operations, matrix operations, etc., is the AMD libraries like RockBlast. So when you do RockBlast, imagine like BLAST, right? Like BLAST operations. So first of all, when you do BLAST operations, don't try to develop yourself some code. Use the libraries. They are the most advanced and efficient for our hardware. So these ones have heuristics that they will understand what to do. If they should use matrix cores or if they should use packed FP32. Packed FP32, I will mention later more details about this. Then there is interesting that not many people using, I would say, or inline assembly. Not currently supported libraries of device functions utilize the matrix operations that can be called from kernels. Also abstraction frameworks, Cocos, Raza, and OCA not supported for calling directly the matrix cores. All of them work for normal operations, kernels, etc. But here I'm talking about the matrix cores mainly, okay? And there is a really nice blog post for AMD matrix cores to understand what's a matrix core, how to utilize, etc. here. So this is a really nice article that got really a lot of attention that how well written and for people that want to understand. Now, the packed FP32, basically, the MI200 GPU has a packed capability for the 3 FP32 operations. Okay, the special instructions that can dump throughput. These new PK instructions allow up to twice the instruction throughput. Packed instructions happen via compiler and inline assembly. So basically, here is an example of a mini hack is a cosmological code that the base was around 22 teraflops and achieved 58, more than double, not just double, more than double. And it was achieved more than double because with FP32, basically it inserts the 32 bits, the package operations into a single buffer and make it like 64 bit, but also with the flow 2, because this is a real data type, right? Flow 2 implementation includes additional improvements on top of the base implementation, including structure of arrays and using the LDS memory. LDS memory is a local data serve memory that's on the compute unit and it's really more efficient than the other memories. So this is a really simple comparison of MI100 and MI250X for the old users of MI100, I would say. The MI100 had one graphic compute die, now have 2 graphic compute dies. Before I had 32 GB of HBM2 memory, now have 64 per GCD, so total 128 of HBM2E. Before 11.5 teraflops were peak performance per GCD, now 26.5 is peak performance per GCD. Before we had 1.2 terabyte peak memory bandwidth per GCD, now it's 1.6. Before we had 120 compute units, while now it's 110 per GCD, so it's a bit less, but powerful. And something really changed. The connection before is on CPU. The connection now is attached on the GPU, not on the CPU. What does it mean? If you do MPI send, it's better the buffer to be on the GPU and not on the CPU. It will work, in both cases it will work. You need some linking and some environment variables to use. And we have also a talk, I think tomorrow or the day after tomorrow, about GPU aware MPI. Now, both GCDs are interconnected with 200 GB per second per direction. You have 120 cycle precision FMA operations per cycle, and now have matrix cores that supports double precision data and memory coherency. This is about using the CPU and GPU and utilize the same memory, the total memory of the server and the GPU, and have coherency. Of course, you pay some cost about memory transfer speed, etc. And there's again a nice white paper that has a lot of information. Now, I like a lot of this plot. It was designed by Oak Ridge. Okay, so basically, what you see here is here's our CPU. Okay, this is the Trento CPU on Lumi, and you see the topology with the GPUs. The Trento has NUMA, 4 NUMA domains. Okay, and if we go to each of them, it has this is the 8 cores, and you see here the core and the threads, because it has threads. Okay, so it's 128 totally threads, but it's 64 cores. Okay, that's why you see these two numbers. So each of these lines connects to one GCD. Okay, to one GCD. So you need to map your CPU process close to the GPU that you use to be more efficient. So if you are here and you use this GPU, and I mean this GCD, you have a long way to go. Okay. Now you see the colors. For example, the blue, that's the connection with the CPU, is 36 gigabytes per direction. 36 gigabytes like that, 36 like that. Okay. The Infinity Fabric, which is GCD to GCD, is 50 gigabytes per direction. So the GCD 5 to 7 has 50 gigabytes per second bandwidth. Now, the 5 to 4 has 200 gigabytes, because you remember it's in the same GPU, so it's 200 gigabytes per second per direction. Now, the 5 to 1, I see has one link, so here is again 50. Okay, so it depends exactly what the 4 to 2 is 100 gigabytes, 50 and 50, has 2 links. So you see that depending on application, mapping is important in order to have quite a good affinity and perform better application. Maybe some applications don't depend really on this, but it's good to have it. And also here you can see the connection, right? The NICs. So it's on the GPUs, the NICs. Okay. And here I have removed something else about NVMEs, because Lumi doesn't have NVMEs, but Frontier has ones. Now I just want to mention that let me go some slides back and come here again. If you imagine this, one moment. Here, this light, here, this hardware. This hardware has 8 shader engines. So what happens is, let me maybe to go to the next slide to explain better. Okay, commands are coming like do this operation, right? So heap says to HSA layer. The HSA layer is a layer that talks directly to the GPU. Okay, it's heap and HSA between the heap and the GPU, and a command is coming and they split it into packages, and the shader engine understands where it should go, because you have to compute units, okay, in 8 shader engines, and the workload manager will decide which of them have enough free computer units to utilize and perform better. So this is the way how it really works. And now I'll show you really simplistic, okay? But the command is coming, and then there's asynchronous compute engines, and the split the workload to small tasks depending on how you call your kernel, and we decided where to load in which shader engine the workload. This is how actually it works. Is there any question? Because I think this was the last one for the architecture. So if you want to... So about this, there's a Affinity talk, I think tomorrow, that explains better and with examples how to do it. Just to mention something, we have activated the low noise mode on Lumi, which means we disable the 0 core. I think it's only the 0. So when you execute stuff, the best is to like OpenAP especially, right? MPI OpenAP is the best is to remove the one core from each from basically the initial cores from all of them. So if you have 64 cores, I use actually, if I remember, 56 I use. So you need to have MPI time OpenAP threads 56 is moment. If you try to use 64 cores, the job will not start. Because with the low noise mode, we dedicate some cores for the operating system to have not to interfere with the application. We have seen some benchmarks. This is better. Now here I didn't say that we have 4 MI250X GPUs. It's 4 GPUs, right? But it has 2 DCDs each one. That's why you can see 8. And with Rock MSMI, you can see the list of the GPUs. So
George, we had a
yes.
question last time on the connecting the NICs to the GCDs, the GPUs, and at the last hackathon, HPE said that there's very little overhead if you're sending a buffer from the CPU through that link. It's negligible overhead for doing that. So I know there was some concern that it might add additional overhead and slow the performance.
Sorry, which link you mean now here?
The network cards off the GPUs,
Yes.
that it would slow down the MPI communication for buffers on the CPU. And HPE said that
okay.
it was almost no overhead for that. I know there was concern at the last presentation we did with what overhead there might be. So it's
Okay.
very, very low.
I had an application, the Nico, that if I was not doing correct mapping, it was not starting. I mean, the initialization was taking forever, and I had to kill it. So I was, I don't know. I would say it depends. Yes, for CPU, but this was CPU aware code. It was not like CPU buffers. But it makes sense, yes. But I think for small, if you do latency test, I don't know. Yeah.
Yeah, they were saying latency would be almost negligible.
Okay.
There might be some situations where bandwidth may not be quite maximum, but it would be rare.
Okay. Any other question? Okay, then we can.
George, let's go ahead and emphasize. George mentioned the GCDs and that they present themselves as GPUs to the operating system. And when you're doing performance presentations, it is really important to be clear what you're comparing, because if you're comparing to a GCD, it's very different than an MI250 GPU. And we get a lot of confusion there.
Yeah, I mean, you had the case that someone was comparing MI250X vs A100, and the code didn't have MPI, so it was only OpenAP offloading. By default, OpenAP offloading will use one GCD, so we use actually half of the GPU. So this comparison is not fair because the first compared one-to-one GPU. So let me.
Can I have a quick question?
Yes.
So what is the bandwidth between the two GCDs? I mean, is it 4 times as the bandwidth between two GPUs as I see? No, what? 2 times?
This is the 200 gigabytes per second per direction.
Okay.
Now you cannot say this is 100, but this is 50. So it can be. Yeah, it's not standard.
Okay, depends. Okay.
Yeah.
But it's 200 give
Yeah,
us?
this is 200, yes, per direction.
Thank you.
Any other question? Okay, let me load the.
George, let's go ahead and get a sense of our audience here. How many of you are new to Lumi? Just raise your hand.
Okay, I started the recording. Yeah, sorry, one moment. We're going to talk about the heap programming. Basically, it's a corresponding of the CUDA for the NVIDIA's heap for AMD GPUs. I'll try to go slow. Please stop me to ask questions. We'll talk about the Radeon Open Compute Platform, the AMD GPU programming concepts, kernels, memory, and structure of host code, device management and asynchronous computing, device code, shared memory, and thread synchronization, GPU software, shared memory, and some about atomics. Now, ROCm, I would say, is our open source software, which is constituted by many components that they all make together and make working on the GPUs efficient on various aspects. Now, it supports, it's optimized training inference model application, benchmarking application support, ML perfects, PLH, PCG, life science, geoscience, physics. Supports many different operating systems, cluster deployment with various Docker and Kubernetes containers, and Slarm scheduler. Framework support Cocos, Rasa, PyTorch, and TensorFlow. Many libraries: Blast, Solver, Rand, Illusion, FFT, Sparse, Thrust. Many of them. No need to read all of them, depending on what you want to do, and we'll mention about this. Programming models: OpenAP API, OpenCL, HIP API. We're not so based on OpenCL. The main, I would say, is HIP and OpenAP. Developer toolchain, compiler, profiler, tracer, debugger, Hipify, and GPU Fort. So we'll talk about profilers later, debuggers also, and the Hipify today. We don't talk so much about GPU Fort. Is a tool that can convert Fortran codes to heap, but it's not. It has some specific conditions to work perfect, so we don't talk about this a lot. GPU device drivers and ROCm runtime. There's deployment tools like ROCm Validation Suite, Data Center Tool, and ROCm SMI. ROCm SMI is a classic command to see like a NVIDIA SMI. Okay, so you can see that it's a lot of components that we try to make it work together. Of course, all of it is open source. Okay, LLVM is behind, and we contributed to the community also, and from the community they try to explore all the ecosystem. With ROCm 5, which is not a new, basically today released the 5.5.0. If you want to check it with, I would say, a really nice change log also. With 0.5, we started supporting also some, let's say, workstation GPUs, and it was installed on some cloud accelerator that we have AMD provides. Optimizing performance with MI200 FP64 matrix operations, as we said, improved cache, improved launch latency, and kernel performance. And of course, we release through AMD Infinity Hub. So if you Google this, you can find container images of various applications and other stuff you can download and even in Lumen use, but they are mainly for a single node, I would say. So the productivity in general will increase with the ROCm 5 and later. Now, ROCm basically it's a Radeon Open Compute Platform. The heterogeneous compute interface for portability, HIP, is part of a larger software distribution called the Radeon Open Compute Platform, or ROCm we call it, the package. The installation instructions here, but I would say that the ROCm usually it depends on where you install it and how can be complicated, so you need to follow specific instructions. ROCm package provides libraries and programming tools for developing HPC and ML applications on AMD GPUs, and all the ROCm environment and the libraries are provided from a supercomputer usually. So there's no need to install something yourself usually, I would say, not always. I will mention later. Now, the heterogeneous system architecture HSA runtime is an API that exposes the necessary interfaces to access and interact with the hardware driven by AMD GPU driver. Now, you never need to write HSA, okay? I just mentioned this here to know what's between heap and the GPU. In some really advanced topics, maybe you would like to see profile some HSA and see what's happening, but you don't need to know exactly and write something, etc. Now, let's talk about some AMD GPU programming concepts. AMD's heterogeneous compute interface, okay, the heap, is a C++ runtime API and kernel language that allows developers to create portable applications that can run on both AMD accelerators as well as CUDA devices. So heap supports both. Something programmed in heap, it will run on both. Some tuning may be required, but it will run. Heap is open source, provides an API for an application to leverage GPU acceleration. It's really similar to CUDA. You will see that basically most CUDA calls become heap and supports a strong subset of CUDA runtime functionality. Now, here, if you have a portable heap C++, if you want to use NVIDIA, you include the CUDA headers and you compile with NVCC to run with NVIDIA. If you want to use AMD GPU, you include the heap runtime, you use HPC, and you run with AMD GPU. It's really simple. You just need to install the heap on NVIDIA GPUs for NVIDIA devices, okay? Now, about the host and device code, okay? Source code in heap has two flavors, host code and device code. The host is basically the CPU. Host code runs here, usual C++ syntax and features. Entry point is the main function. Heap API can be used to create device buffer, move data, etc. So the heap calls are called from the CPU to tell the GPU what to do. So the device is a GPU. Device code runs here, usually it's like C-like syntax. Device codes are launched via kernels. Instructions from the host are enqueued into streams. We'll mention what streams later. There is a lot of API. This is one is really small set of API. If you know CUDA, you know, for example, that there is CUDA set device command. Now it's called heap set device. Heap get device, heap device properties. So heap set device says which device to use. You remember the GCD 0 to 7, 8 GCDs. You can define here which one to use, for example. Okay, or get information from one of them. Memory management. Heap malloc. If you know programming, the malloc is allocate memory. The heap is the allocate memory for the GPU, right? Heap memory copy memory between two source and destination. Copy memory asynchronously to overlap with something else, for example. Or free the memory, right? Heap free to free the memory on the heap. Now streams, as I said, I will have slide later. We have the possibility to run many streams concurrently to overlap phases, computation, communication, that it is possible to overlap from the algorithm point of view, from the science, etc. So you can create streams and make them run different kernels that don't depend to each other. And of course, you need some moment to synchronize the device or the stream or destroy the streams when you finish them. And with events, you can create events for time purposes, to track the time, to record events, to wait for a specific event, and to measure the time, the elapsed time. device globals, device kernels, the global is for the kernel, for the device of a device code, and this one is an old way to call a kernel, heap plus kernel, GCL, and the arguments. Now, the device code is thread.dx for thread, the block, the dimensions, the shared memory. There's more than 200 math functions covering entire CUDA math library. And you can do error handling with heap get plus error and heap get error string. It's really good to check about errors also. Before I continue, any question here at this point? Okay. So, yes?
I had a question.
Okay.
So are the streams similar to like, so when you say like one MPI process can access like half a GPU, so is it like can it be subdivided further? Is it
And stream, no, this what you say is possible, but streams is about I do MPI communication and on the other stream I do computation, so to overlap computation with communication, something like that.
okay?
It's not to split the GPU. You can run by bare metal many API processes on the GPU on one GPU. So one GCD is not only to run one API process. If your application is more efficient to run 2, 3, 4, and even more API processes, you can just start and run. And you don't need, if for the people who know the CUDA stuff, you don't need the MPA stuff. You need to start for CUDA to run more than one API process per GPU. It can run by default more than one. But this depends on the application, so I cannot say, and it's not stream related. Stream is about to split it during the timeline, I would say, not to split the GPU.
Okay, yeah, that clears. Thanks, you.
Okay, so if no other question, I continue. Kernels, memory, and structure of hosts. So in heap, kernels executed on 3D grid. This is the same for all the GPUs, I would say. You might feel comfortable thinking in terms of MS points, but it's not required. The grids, let's say it's what you can map your problem to, right? It's not a physical thing, but can be useful to think like that. AMD devices support 1D, 2D, 3D grids, but most work maps well to 1D. Each dimension of the grid partitioned into equal size of blocks, and each block is made up of multiple threads. So this is really the same concept with the CUDA. The grid and its associated blocks are just organizational constructs. The threads are the things that do the work. Sometimes we call the threads work item for AMD GPUs. So grid and block structure is very similar in heap and CUDA. And basically this is the terminology that we use in CUDA, heap, and OpenCL, but here we don't talk about OpenCL. And okay, grid and block, thread. The big difference is the warp and wavefront. Okay, the warp in a CUDA is 32, in a heap is 64. So basically, let's say it's the latest, with simple words, the latest level of how many threads do some workload concurrently that moment, or at least try to. So it's 32 in CUDA and heap is 64. Now, imagine a grid blocks of threads in 1D, okay? Threads in grid have access to the respective block IDX. This is the block. The thread ID, the respective thread ID in a block thread ID. So thread IDX is one of these threads here. If it is for threads, one of them. The block dimension, okay? How many? How big is this block? And the number of the blocks in this grid, the grid dimension. Okay, so there is the thread.dx is a thread, which block, dimension of block, and dimension of the grid. And here it is the same in 2D. Each color is a block of threads. Okay, each color like that, is a block of threads. Each small square is a thread. 1, 2, 3, 4. The concept is the same in 1D and 2D. In 2D, each block and thread now has two-dimensional index, right? X, okay, Y, etc. So you have two dimensions. The difference is now you call block idx.x, block idx.y, and similar for block thread idx.x, .y, etc. So you have more dimensions. It's not always necessary to do that or to use like that. So let's see an example. Okay, a simple parallel loop. This is This is a loop that I hope everybody understands that this is n iterations, and we take this array and we multiply for times 2. Okay, its value times 2. This can be translated to this one, and let's see. A device function that will be launched from the host program is called a kernel. It's declared with a global attribute. Okay, a kernel starts always with that. Kernels should be declared void. Okay, all threads execute the kernel's body same moment. Okay, now this is, you name the kernel as you want, and this is the arguments that you want again. So the only mandatory is a global void, and then whatever the kernel requires as input and what to do, and what it has to do. Each thread uses unique thread and block IDs to compute a global ID. So I is my thread, and also how many blocks have already gone behind this thread. This is the way to calculate where I am in the global position. This is the global ID. Here says if the thread, the number of the threads, the ID, is less than n, do this. Okay? Sorry. And this is the way you make this to here. Now, as you see here, now the array is called d_a because this is now on the device and not on the CPU, okay? On the CPU memory. This is on the host, this is on the device. A good approach is when an array, a variable, whatever is on device, we use a D in front to remember that this is for device, etc. Now, kernels are launched from the host, and there's 3D dimensions of a block of threads. Now, this is a block of 3D dimension of block of threads because X, Y, Z is the dimension, but usually, for example, we use only one dimension. So we only use one dimension, 256 threads per block. Okay, and this is the dimensions of the grid of blocks, and usually we take the problem size of the, okay, and we see the blocks, the problem size, and we divide it by 256 to find the appropriate block size corresponding to the number of the threads. Again, for one dimension. And how we call the kernel? We give a name of the kernel, like CUDA, blocks, comma, threads, 00, and the options of the kernel, okay, the arguments of the kernel. Now, the older approach, if you have used AMD GPUs all the time, it was the heap latch kernel, or you call my kernel blocks, threads, okay, 0 for bytes of dynamic LDA space, 0 for stream, this is the default null stream, and kernel arguments. Now, this thing is converted to this. Okay, and now it's more easy support for the other. Also, when you port your code, is the default, is similar. So, seeing the operations why blocks and threads. Natural mapping of kernels to hardware. Blocks are dynamically scheduled on the compute units. All threads in a block execute the same compute unit. Threads in a block share LDS memory and L1 cache. Threads in a block are executed in 64 wide chunks called wavefronts. Wavefronts execute on SIMD units. If a wavefront stalls, computer units can quickly context switch to another wavefront. A good practice is to make the block size a multiple of 64 and have several wavefronts. Something to mention here, but although it's not the moment, threads in the block share LDS. So this memory is the fastest memory of the GPU, and it's really small, it's a few kilobytes. And if you use all of it with one block, you cannot start utilizing with another block the GPU, so you can take worse performance. So the concept is here to know your hardware so you don't make it stall waiting to finish something else, etc. that you utilize, and you should not utilize so much because you need resources to utilize your compute units also. Device memory. Okay, here's an example. Integer 1000. Okay, it takes the number of the bytes of n times of the double. And the host memory means the memory on the CPU memory, okay, we define it as HA, double, malloc, and bytes. While to allocate on the device, we say the device A equal null, and we do heap malloc. Okay, this is the number of the bytes. And of course, in order to free them, the host is like the classical free and the other is heap free. So there's differences. Any question here? Okay.
Yes. What is going to happen if you do not free the memory?
Honestly, nothing except when you have, except if you don't have enough memory anymore. So if you have any iteration here, allocating more and more, and you don't, maybe you will get out of memory. And also, it's not good practice not to free the memory, right? I mean, you should free, but you are in risk that your program can fail for memory issues. But if there is enough memory, maybe you will never see it actually, if it's more toy case, maybe. It depends on the code, I would say.
Thanks.
Now, device memory, the host queues memory transfer. So for example, copy data from host to device, heap memory copy, and for example, the device A, host A, bytes, and here heap memory copy host to device, host to device. So this will go here. Copy data from device to host. Let's say you want to return some results. Memory copy device to host, okay? So device to host. Copy data from one device buffer to another one. So these are both in GPU device buffers. Memory copy device to device. So you can do whatever you want basically, recording of the memory transfers. Now, can even copy started sections of arrays. Now I have never used this heap memory copy 2D. Pointer to the destination. Bits of destination array, pointer source, a source array, number of bytes in each row, number of rows to copy. So this is about to like a small part of the array to be copied. So it's like slided sections. Error checking. Now, it is important to do that. Why I'm saying that? Sometimes application fails, you don't know why, and some allocation or whatever else has failed, but you didn't have this warning and you have to debug, etc. So most heap API functions return error codes of heap error underscore t. For example, heap malloc will return the status. Heap memory copy status. If your API function was error-free, returns heap success. Otherwise, it is an error code. We can also pick get at last error return. So if we do that, we say heap get after this, for example, we run this get last error, pick last error. Now, we can get the corresponding error string using heap get error string status. So this will print a message we'll understand. So we can define a macro, heap check, which says here this heap error t status equal command, and say that if status is not heap success, then print error heap reports and heap get error string status. So this way, you can always do heap check the command and see if something works or not. Now, if I remember correct, the difference of these two is that the get last error will pick the error, and it will clean it, while this one will keep it active until you do something. So if we do putting this all together, we have this as before, if you remember, the 1000, the malloc, and now we say heap check, heap malloc. I say heap check, heap memory copy. And I say my kernel, okay, launch kernel, and heap check the get last error. If get last error means did the kernel launch it correctly or there was an error. And heap check, heap memory copy, for example. So this is a really nice functionality to check if something was wrong or not. And of course, freedom here. Yes, also the kernel is the same classic kernel here. And how is this defined, the heap memory check? Is this here, this macro. Now, vector addition. Let's discuss an example. So vector addition is like you have one vector, add it to another vector, equal this vector. This example is 16k times 16k, 16 blocks for x and y dimensions and 1 for z dimension. And this is an example code, host ABC, malloc, this float, data type, okay, number of floats, etc. Heap malloc, device ABC, 3 arrows, again with float. Now, if you observe here, we have a double pointer because one of them is about retaining the error status, etc. Heap memory copy, device B, so this is host to device, so host to device, host to device, host C to device C. So we copy B and C only, but why only B and C? Because it's like A equals B and C, so we need the B and C to calculate the A. And I have here vector, the kernel, vector add float. And this is, yes, this is the problem divided by threads per block, and the heights divided by threads per block in the y-axis and he direct dimension and y dimension, and how many threads per block per dimension again. And here's the options that it uses. And also heap memory copy from device to host. The A is a result, and you free the device A, B, C. So do you want, I want a bit back, you want to ask something, you want to have a question on this? So this basically, we define 3 arrays on the CPU, 3 arrays on the GPU. We copy only the 2 because the last one is the vector addition basically from the other 2. So only 2 are needed. We call it basically, we divide it based on the threads per dimension. Keep a memory copy, verify the results, and then free the device stuff. Also, here we need to also free the host A, host B, and C, right? It's not here. Any questions, something that you need to ask? So, vector addition profiling. Profiling will be later, I think it's on last day on Friday. By default, ROCm has installed the ROCprof. It's a profiling tool, the basic product that we have. And if you do stats, heap trace, and your executable, it will print you the kernel names, the heap commands, the kernel names, plus the percentage that they take of the total duration. So you see here, heap memory copy takes 99.8, almost 8% of the time of the application. So memory copy basically takes most of the time. So it's really easy to understand what happens in your code. And here you see the average, because here there is 3 calls, total duration and average duration. Sorry. So here we have the perfetto. The perfetto visualize. So from here we can create a JSON file that you can load with the browser. We'll see that on Friday, and you can visualize. And you see here, here's the time. Okay, the time, various events. See here you see heap memory copy, heap memory copy. You can see the activity of the CPU, and here you see the GPU activity. That can be any kernel running, etc. So you can observe visually what happens in your code and understand if something is good or bad. Any questions before? For profiling, we have extended sessions on Friday, so don't worry about it. Okay. Device management and asynchronous computing. So device management is about multiple GPUs in system, multiple host threads, MPI ranks. What device are we running on, for example? How you can query number of devices visible to system? You define the number of devices integer or whatever you want, and you take the get device count, heap get device count. So you can know how many GPUs is in the system. So you can make it automatic on your software to divide your workload per X devices that are available on the system. Host tells the runtime to issue instructions to a particular device. So you can say device equals 0 and set device 0. Then this will use the device 0 only for the following code. This way you can play later and see, you can play with an API and word rank, etc. to use multiple GPUs. How can query what device is currently selected? Heap get device and device ID to understand which device you are running. The host can manage several devices by swapping the currently selected device during runtime. Different processes can use different services or oversubscribe the same device. Okay, so you can use multiple devices per GPU. Device properties, basically the host can also create device properties like that. You take device properties from device ID. So this is a structure that contains useful fields like the device name, total VRAM, clock speed, architecture, etc. And there's plenty of information in these header files. Yeah, blocking vs non-blocking API functions. Latching a kernel is a non-blocking. After sending instruction data, the host continues to do more work while the device executes the kernel. Multiple kernels latched on different streams can run concurrently on the same device. Before I continue, now mentions this. If you latch a kernel and you demand you take the output of the kernel in the next step without any blocking mechanism, probably the result will be wrong because you need to block the kernel to finish and then take out the result. However, heap memory copy is blocking. The data pointed to the arguments can be accessed and modified after the function returns. So if you do heap memory copy, it will wait till it finishes to continue running the code. To make asynchronous copies, we need to allocate non-pageable host memory using heap host malloc and a copy using heap memory copy async. So this way, they can make asynchronous heap memory copies. Heap host malloc is about number of bytes. Heap memory copy async is host to device and bytes a stream. Now, here we have now the stream, right? Which we can define streams to execute on separate streams to overlap with the other commands. It is not safe to actually modify the arguments of heap memory copy async without some sort of synchronization. Okay, so this you don't know when it finishes if you don't make a check if it finishes. So you need some synchronization mechanism before you take the value. So again,
George,
yes.
George, from the performance point of view, the synchronous or asynchronous are similar in terms of performance.
I would say yes. The asynchronous, you use it only to overlap. So when I can do a memory copy as asynchronous and I can run a kernel that doesn't depend on the data that I'm sending or want to receive, I can send this to a stream and at the same moment do another run another kernel at the same moment. So I overlap and the execution time decreases.
But the single stream has the same speed, roughly.
I will run the stream. I will run the kernel to different stream. So this goes to its own stream, and I will run the kernel to another stream to make it overlapping.
I got it, but the single stream has the same speed, roughly.
Sorry, the single stream has?
Well, if you have multiple streams going at the same time, the bandwidth is the global bandwidth divided by the streams, the number of streams.
That's why I said kernel. I didn't say memory copy. Yes, with memory copy, yeah, you will divide it.
Okay, fine, thanks.
Yeah. Okay. So now if we put all of this together from the previous slides, you can see now how the heap check, malloc, memory copy, get last error, memory copy. Now the host waits for the kernel to finish here. Okay, so this, the host will wait for the kernel to finish here. Now let's see streams. Let's talk about the streams now. Stream in heap is a queue of tasks, kernel memory copy events. Tasks enqueued in the stream complete in order on that stream. So first enter in a stream, specific stream, first exits. You cannot change the order of the events that happen in the stream after each of them is inside the stream. Tasks being executed in different streams are allowed to overlap and share device resources. Okay, so if you run so many streams that there's no compute resources for the GPU, of course, some streams will be blocked, will not run till some resources are freed. Okay, so always you need to have it in your mind, this thing. Now, how we create a stream? we define like stream, heap stream data type, and create like that. So we create like that, and you can destroy like that. Okay, heap stream create, heap stream destroy. Passing 0 or null at the heap stream t argument of a function instructs a function to execute on a stream called the null stream. No task on the null stream will begin until all previously enqueued tasks in all other streams have completed. So, I repeat, if you put something in the null stream and you have other streams, this will wait to finish first the other streams. Blocking calls like heap memory copy run on the null stream by default because it's also blocking. And let's see this example. Let's say you have 4 small kernels to execute, right? 1 dimension, 256 threads, and the arguments for the kernel. My kernel 1, 2, 3, 4. Even though these kernels are using 1 block each, they will execute in serial on the null stream. On the null stream, you will call my kernel 1, then 2, then 3, and 4. Now these are visualized perfect. Maybe there's also a gap between the kernels, but this is a sequence that will be ordered, and this is the time that it will take. It will take significant time. It depends on the workload, of course, but they are serialized. Okay, and as you see here, I have nothing. I have 0 stream for all of them. Now, let's say I create 4 streams, stream 1, stream 2, stream 3, stream 4, and I call them again the same but with streams. Now what happens, this is my null stream, and this is my new streams, 4 streams that they will overlap. This overlap here seems perfect. Usually, okay, it's not perfect, right? It's starting my kernel 1, and maybe a bit later kernel 2, but they overlap. But maybe not 100%, maybe less. Kernels must modify different parts of memory, okay, here, to avoid data races. You need to modify different parts of memory. With large kernels, okay, if this is really large kernel, overlapping computations may not help performance, because if this takes half GPU, this half GPU, then there's nothing for us to do. They will wait for them to finish before they can do something. That's why when you make streams, you need to have in your mind that, okay, am I doing that correct or not? There's another use for streams besides concurrent kernels, overlapping kernels with data movement. So AMD GPUs have separate engines for host to device, device to host, and compute kernels. These 3 different operations can overlap without dividing the GPU's resources. They don't divide the GPU resources. So it's different the bandwidth going, different coming, different compute, okay? I don't share the bandwidth of hosted device between these 2 because they have different. The host memory should be pinned, okay? Pinned memory. Host data locations are pageable by default. The GPU can directly access host data if it's pinned instead. How we pin is we do this heap host malloc. So we know exactly the memory location and it's faster the memory transfer, like that. And how to free the pin host memory, heap host free and the memory. Host device effective data rate increases significantly when host memory is pinned. It is good practice to allocate host memory that is frequently transferred to from the device as pinned. So I would say don't do pin memory if you do data transfer once or twice, but if it's happening really often, yes, do it. And here we have some streams, heap memory copy, okay, heap memory copy, 3 of them, and you can see it here. This is hosted device 1, host device 2, host device 3. Then kernels, 3 kernels, and 3 device hosts. Okay, so you can see here they're serialized in the null stream. I have used no streams here, and they're like that. Now, changing to asynchronous memory copies and using streams. So you see here, I use streams here, 1, 2, 3. Here I use streams in kernels 1, 2, 3. And here again, from device to host, 1 to 3 streams. And what does it here? Host to device 1 starts. Because this is not shareable with this, it's hosted device, it's the same bandwidth direction. This will start after, okay? And my kernel starts here, my kernel 1. Device to host finishes here and overlaps with my kernel 2, and then runs the device to host 2, which starts the host to device 3, my kernel, and device to host 3. So as you see, there is some overlapping, but also it's not a perfect overlap because these three don't share the same bandwidth, etc., as we said, to decrease the resources. Now, how to coordinate execution on device streams with the host execution? The heap device synchronize is heavy duty sync point, blocks host until all work in all device streams has reported complete. While the heap stream synchronize blocks host until all work in stream has reported complete. So this is for the device, for all the device streams, while this is for the stream. So it's a big difference. And you need to know what you want to synchronize. Can a stream synchronize with another stream? For that, we need events. So a heap event object is created on device. We are like that. Heap event create. We queue an event into a stream, like that. The event records that work is currently queued in the stream. When the stream's execution reaches the event is considered complete. Okay? And at the end of the application, event object should be destroyed. Heap event destroy the event. So this is to record just that an event happened. Just that. So what can we do with queued events? Heap event synchronize block host until event reports complete. So imagine a workflow application that you need to wait for something to happen. You need to do is like a workflow and block something until this operation happens in somewhere. Only a synchronization point with respect to the stream where event was a queue. Okay. So this is about the blocking for this event in this stream. This is a classic one. Heap event elapsed time. It measures the elapsed time. Okay, returns the time. Okay, between the two events, start event and end event completed. Can be very useful for timing kernels and memory copies. While heap stream wait event, you define stream and event, non-blocking for host, instructs all future work submitted to stream to wait until the reports complete. Primarily, may we enforce an ordering between tasks in separate stream. So we can wait here, it's no blocking, and it asks all of them to wait. And here's something with streams, okay? Local compute kernel is like that, compute stream, we call it compute stream. And copy data, heap memory sync to data stream. Wait for data to arrive, heap stream synchronize data stream. Wait for data to arrive. Exchange data with API data exchange. Send new data back to device. So my kernel is running. Okay, device to host is here with the stream synchronize. Okay, API happens, and here memory copy from hosted device. And the API is here happening. So this way we overlap computation with the data transfers and some API. Is there any question?
Yes, why the my kernel, the green task goes beyond the H2D?
This is nothing. This is visualization.
Got
Let's say this takes enough time. I mean, that's all. It's not really. It could be finished earlier also, indeed. Yeah, it doesn't matter.
So ideally, the my kernel should terminate at the end of the H2D.
Yes, but I mean, the reality can be also that long, right? Also, I mean, here it's not about really the duration, more than the overlapping, I would say. Here can finish here indeed, but yeah, I mean, doesn't really matter, I would say. What matters is to overlap, to make it all of this concurrently. Because otherwise, if you don't do streams, all of this should be added here, right? So it's extra duration.
And I assume that you can have different streams on different devices with different timings.
Different timings? What do you mean?
Length of the process, of the MPI processes.
Yeah.
Okay.
Mm. Now, with the GPU over MPI stack, the host device traffic can be omitted. So some synchronization so that the data GPU and local compute are ready. Have a heap device to synchronize, API data exchange. I call the compute and then wait. So in that case, you see here that when my kernel runs, a part of this is the MPI because it's a GPU aware MPI. So it can just start working and be able to overlap. That's why the GPU aware MPI is quite more efficient in many cases compared to being on the host and block it. Now I'm wondering if we need a break or not. I don't know the program, but okay. So now when you use HPC, makes two compilation passes through source code, one to compile host and one to compile device. Okay. The global functions, these are the entry points of device code called from the host. Code in this device will execute on SIMD units. Device functions can be called from global and other device functions. Cannot be called from the host code. Not compiled to host code and essentially ignored during host compilation pass. Now, if you do host device functions, can be called from global, device, and host function. Will execute on SIMD units when you call from device. So these ones are about how we declare some functions, kernels, how you want to call it, and from where they can be called depending on the case. And I have seen many people use host device functions, etc. SIMD execution. On SIMD units, we are aware of a divergence. Branching logic, if else, can be costly. So we try to have less branching. Wavefront encounters an if statement, evaluates condition, if true continues to statement body, if false also continues to statement body with all instructions replayed with no ops. So we'll do nothing no operations for the other threads, known as thread divergence. Generally, wavefronts diverging from each other is okay, but thread divergence within a wavefront can impact performance. So between wavefronts is okay, but not inside. You will pay for it. So this is an example. I have a simple execution, right? And it says here modulo 2, for example, is that, or else it's this. So then you will see that this is how we converted that if here is not true, no operation, else do that, while here, if it's true, do this, else no. And this is how we split it, really the wavefront. Memory declarations in device code, malloc free, not supported device code. Variable arrays can be declared on the stack. Stack variables declared in device code are allocated in registers and are private to each thread. Okay. Threads can access common memory via device pointers, but otherwise do not share memory. Important exceptions: shared memory. With shared memory, the LDS, how we call it, is memory that shares between the threads in the compute unit. Now, stack variables declared as shared allocate once per block in LDS memory. Shared and accessed by all threads in the same block. Access is faster than device global memory, but slower than register. Must have size known at compile time. Okay, at compile time to know the size of this declaration.
How much slower is it to access shared memory and then registers? Do you have a number there?
No, I can tell you that shared memory could be like 15, 17 terabytes per second. Of course, you don't have so much, right? You have some kilobytes.
Yeah, sure.
From register, I don't have something. I don't know if you have, and I don't know if we give for allowed to say. I don't know that, to be honest.
It should just be a cycle or two, so it's very fast.
Yeah.
Mm.
Now, shared memory here is like you have a defined kernel, okay? And it says shared memory, this array of doubles shared in this block, okay? So I have 256, so I annoyed the number during the compilation. And I say as defined a TID, thread IDX, and basically each thread fills one entry, right? I say the SITID equal the task and assignment. And then I write out array in reverse order, right? And I do this for reverse order. And basically we'll call this the reverse kernel. So in this way you use the LDS and to reverse something. This is a really toy example, of course, right? That is much more complicated things to do. And this way, you can use the LDS to do something quite fast. And something is missing here. The sync threads, in order this to be safe, okay, before you access again, you need to synchronize the threads in the wavefront, right? And this is the command sync threads to synchronize the threads. If you forget this, maybe this has not finished totally, and you can get the wrong data basically. You should be really lucky not to get something wrong. Thread synchronization. Sync threads is blocks a wavefront from continuing execution until all wavefronts have reached sync threads. Memory transactions made by thread before sync threads are visible to all other threads in the block after sync threads. Can have a noticeable overhead if called repeatedly. So don't try to play with this a lot. I mean, try to be careful how many times you call it when you call it. Best practice: avoid deadlocks by checking that all threads in the block execute the same sync threads instruction. So long as at least one thread is in the wavefront encounters sync threads, the whole wavefront is considered to have a counter sync threads. And wavefronts can synchronize at different sync threads instructions, and if a wavefront exceeds a kernel completely, other wavefronts waiting at sync threads may be allowed to continue. So this is about a bit more, I would say, complicated situations that it's better sometimes to avoid to get into that. Because I would say that's easy to lose control also what's happening. Now, GPU software, shared memory, and some atomics. Now, how to compile a code with HPC, right? HPC is a wrapper basically. It's a Perl script, etc. Inside in the ROCm, and you can say offload architecture. What architecture? CFX90A. What? This is my C++ file, and this is my binary. In this way, you compile a heap application easily. Now, if you set HPC verbose equals 7, you can see a bunch of useful information like compile and link lines, various paths. So for example, if I do like that, this is an order command, I can see where's my heap path, platform, command, options, etc. You can also use HPC-v to print some information. With the command heap config, you can see many information about the environment variables declaration also. Now, I don't know if this, now inspecting this one, I don't think, one moment to see something. Yeah, I don't want to have this here because it's too much. Now, if during your compilation, you do -g for debugging and save temps, okay, these output files into the current directory and the assembly can be found like that if you have a vector add heap binary, for example, something like that. Also found are the compile time estimators for registers and scratch size and occupancy, so you can see information about registers here. If kernel is templated, then assembly is generated for the various installations of the kernel. Okay. Now, I will not talk here about ISA because it's a complicated topic. They have some good PDFs. I just want to show you here this command, for example, and how to take the vector addition in ISA command from here. You can take a lot and see what happens. Now, usually in this, you focus to a kernel to see what's going on, but it's useful to take the registers to see how many you use, if you use too many, etc. This is a good indication of how good or bad is the kernel also. But I don't want to talk about the ISA here. Now, querying the system, ROCm info queries and displays information on the system's hardware. Querying ROCm version, you can do this to take the version that's displayed. ROCm SMI queries and sets empty GPU frequency. So here I have reserved one GPU only and says, for example, temperature, average power, percentage of GPU 0, so I don't really use it. Power cap, performance. This is performance manual. This is usually Bioto, etc. Fan, etc. So usually with full node, you will see 8 GPUs. Now, ROCm GPU libraries. Typically, there are two versions, let's say. You know from CUDA the QBLAS, okay? Here, if you use HipBLAS in your code, then when you compile it with HipCC or NVCC, it will use QBLAS or ROCBLAS, depending if you use AMD hardware or GPU hardware, okay? So this is more, HipBLAS is more portability. ROCBLAS, if you use ROCBLAS, is less portability. Maybe you save some performance, although we haven't seen haven't seen even significant performance difference. But maybe you can see, I don't know, 1, 2, 3%, something like that sometimes to use directly the ROC library. Again, we have a lot of libraries, basic linear algebra, fast4Em, random generation, C++ parallel algorithms, optimized parallel primitives, and sparse blast, linear solvers, solvers and preconditioners. And you can find here a great heap porting guide for the complete list also of the libraries. Now, here, yes, if I remember well, the libraries are not properly installed automatically anymore. I think all the time we have to install the libraries ourselves, not ourselves, the support of the supercomputer. So this is for a really demo for the installing locally on your desktop if you have something with AMD devices. To show you how simply it was to install on Ubuntu, etc. However, it's really easy to install it also on your any system. But maybe almost you need root access to some system, so the support will do it for you. But I think they have done it already. I hope at least.
Yeah, it should be in this default set of libraries.
Yeah. So yeah, this is an example. So I hope this link, I'm not sure if it's still the same, a documentation for level 1 to 3 functionality. Rock Blast matches Blast closer than Heap Blast or Cube Blast. Use Heap Blast only if you need portability between AMD and NVIDIA. And you can link with L Rock Blast. This usually is in the ROCm installation, the libraries, okay? And here you can see how there's heap malloc, heap memory copy, but this rock blast to make the handler, to create the handler, the status, rock blast DACP to do, I think this is double precision A times X plus Y, destroy, and take the results and free the memory. So it's really straightforward, like you will do with blast, etc. And of course, we have, you can find here, it's again, everything is open source, right? So you can find a lot of information on various links about the libraries. RockFFT, HeapFFT, and no need to read all of this. You can find in the slides. Of course, we have AMD machine learning support, TensorFlow, PyTorch a lot. MIOpen, we're working on the Rickle a lot, even on Lumi, Benchmarks, MLPerf. There's a lot of work happening on this. So again, there is a lot of work happening and it's open source. This is, I think, okay. Dynamic sized memory can actually use set arrays when sizes aren't known at compile time, called dynamic sized memory. Declare one array using heap dynamic set macro used for all dynamic LDS space. Used during the kernel call, and we haven't discussed that yet. So basically, we have the reverse, and we'll do this heap dynamic cert, okay, like that. Instead of the dash cert before, heap dynamic cert. Again, it's the same, and we'll do here the size of. And this is how you can do when you don't know that this is 256, for example, like before we knew that this is 256. And atomic operations, atomic functions. Now here it depends on what you want to do. Perform a read write of a single 3264 byte in device global or LDS memory. Can be called by multiple threads in device code, perform in a conflict-free manner. We support atomic operations on 32-bit integers in hardware. However, just to say, I'm not sure if we have it here, there's a flag that improves a lot the performance of atomics because it costs also a lot, I would say. And there is support atomic operations in heap. Adds, replace, bitwise and or XOR, etc. So there's plenty of them. Again, it costs, and I would say that with this unsafe variable, we have seen improvement in the performance or using atomics. Now, resources, you can find the Rocket platform, the HIP porting guide is here, about libraries, Rock Profiler, we have new profiling tools also that we'll show you on Friday, and the ISA docs and more are here. We try to improve the documentation in all aspects, but still it's a work in progress, I would say, although there are some stuff. Now, this one, I don't know if it's 100% updated. CUDA features not supported by HIP. Dynamic parallelism. This one, I'm not sure if it's supported yet. QPTI not directly supported. I will use an alternative. Managed memory, this should be, I think this support now anymore. Because this information could be old now. Page migration, including CUDA mem advice, CUDA mem prefetch, or other not supported. I think so. But anyway, in this link, it's a bit late, I hope it's still valid. It's about what specific version of CUDA does HIP support, okay? So you can see all of them, what's supported, what's not supported. I would say something clear that if today a CUDA is coming with a new feature, HIP is not ready. Usually we need some time before HIP supports a new CUDA feature. And of course, sometimes if it's possible because of some hardware differences. So someone who uses the latest CUDA features maybe did have more complicated to port, etc. Then HIP is an extensive API that covers a lot of GPU programming requirements. It's under continuous development. As I said, now 6 hours ago, we have a new ROCm stuff. It can be executed on AMD and NVIDIA GPUs. We can have profiling tools that can identify bottlenecks. And as I suppose some of you know the AirSight tool from NVIDIA. Now we can have roof lines also on AMD GPUs, etc. We'll see that on Friday. It's quite easy to use, especially with previous GPU programming knowledge, right? If you know CUDA, many things are really close, I would say. So that's all for me. Any question here? Bob, how are we going with the schedule?
We're a little behind, but just a minute or two, just a couple minutes. So I think what we'll do is start the exercises. We have exercises plus we may take the break early after the exercises. So I have just posted the HackMD site, which has the instructions on how to go through the exercises with HIP. If you are having trouble connecting, send me a private chat message so that we're not taking up the whole group, and I'll work through problems with you. It can be a little tricky connecting to Lumi for your first time.
Yeah.
I don't know, Bob, should the record the hands-on or not? I suppose, I don't know. So,
I don't think we need to record the exercises.
no, right?
Right.
Okay.
So HipFort is basically designed to use the HIP C calls from Fortran. Normally you would have to provide an interface to the HIP kernels, the HIP libraries. So how do we do that? We're going to wrap the functions in a and make them accessible from Fortran through the ISO-C bindings. It can be a little tricky creating an ISO-C binding, so HipFort does that for you. And you know, there's a couple different implementations of it through HipFort, and depending on the Fortran standard level that you're using. So there's an interface with 2003 Fortran and also with Fortran 2008. And with this, you can still run both on AMD and NVIDIA GPUs. If you use the ROCm interfaces, that only runs on AMD GPUs. And AMD is committed to portability of code, so we do encourage you to use the HIP interface where you can. So HipFort is part of the ROCm software package, but it's not installed until version 5.4.0. We are running 5.2.3 on the Lumi system, so you have to install it if you're going to be using it. There are install instructions in the HackMD, and you know, I'll go through that a little later. If you need to do a user install, then you're going to want to add the bin location to your path so that it can find it, the include path and the load library path. There is no HIP equivalent to CUDA Fortran. So if you have a CUDA Fortran code, you're going to have to do some more work to call HIP functions from your code. CUDA Fortran is not a standard, so you know, there is no standard interface for that from the AMD software stack. And so you would normally port your code to call the HIP kernels directly rather than write it in the Fortran code. And then you use the ISO-C binding to call the HIP functions. So that is standard conforming Fortran. It should be portable, and almost all the functions in the ROCm stack are available through the HipFort bindings. So let's look at what happens there. So here we have a launch kernel. We're going to wrap it in a function called launch, and we're going to make it extern C so that it's got a plain link name to be called from Fortran. And then you see this interface using ISO-C binding. So we see this ISO-C binding call and that use statement, and that will allow us to build an interface for Fortran. And so now we can call launch, and it will basically have an interface to calling the HIP launch kernel. So we can add that call now to our Fortran code directly and call it as if it were a Fortran routine. To install HipFort, you have to set the directory you want it to be in. Then you do a git clone, then a fairly standard build. You'll make a build directory, cmake, make install, and then you have to set your paths. And if you want to do this and test it, make sure your installation's right. Here's a quick little example you can use to test the installation. And the example is in the HipFort source that you downloaded with the git clone. So I would suggest you test that before you start putting it into your code. Make sure your installation's correct. So there's a couple different references that you can go to learn more about HipFort. Joe Schoonover was one of the original authors of it, and he shows how to use it as part of the AMD Lunch and Learn series. There's also a really nice presentation by Alessandro, one of our staff members, on using HipFort. And so it's a fairly straightforward process if you're working in Fortran to call the HipFort. So where would you use this? Well, you might be trying to call, some of the HIP laws or HIP FFT. And so this allows you to use those routines directly from your Fortran code. Okay, so that was just a brief talk about HipFort. And now I'm going to bring up and talk about porting applications to HIP. Okay, so let me just make a quick check for the chat. Okay, no questions there. So let's talk a little bit about porting applications to HIP. This material has been created by, again, quite a few of our staff. And the idea here is to make it easy for you to take an existing code and convert it from CUDA to HIP. And we call that process HIPifying. And there's two tools that you can use for this process. You've got HIPify Perl and HIPify Clang. And HIPify Perl is the easiest to use. And it works just as well as HIPify Clang for most applications. And it also is much easier to use. The HIPify Clang, you have to have the CUDA headers. So HIPify Perl is what we tend to use the most. And it's basically a string replacement. You replace the CUDA with HIP. And there's some special cases that they handle for libraries or other situations where the CUDA keywords need to be replaced. And basically, something like a CUDA memcopy becomes a HIP memcopy. So it's nearly a one-to-one translation. Now, once you get it in HIP, you can now compile it through CUDA for an NVIDIA GPU, or you can compile it for an AMD GPU. So this gives you portability. And we've even had some sites that have installed, that are using NVIDIA GPUs that have installed HIP so that some of their applications could develop portable code. So there are a few cases where it cannot do the translation from CUDA to HIP. and we'll talk about some of the different situations that you might encounter that fall into that category. Hippify Clang is a compiler-based version, so it's really parsing your code. It can do a better job. And there are cases and some applications where that is a better tool, especially if you're doing something a little bit more extreme with your CUDA code. And so if you want to use that, you have to build a Clang compiler version of Hippify. So what's the what does this process look like if you're in the planning for a code port? I've heard this conversion process being described as a half day's work, and that may be a little exaggerated, but it's actually pretty fast. And we have examples of code conversions that have been reported. 80 to 90% of the work is generally done by these Hippify tools. Here's a couple code examples where they cited how much was converted automatically. But it's really dependent on your code. If you're doing something really complex in CUDA, or using low-level CUDA code like PTX code, it's going to require more manual work. I do want to warn you that actually adapting the build system can take more time than porting the code. And some of this is dependent on your build system. If you have a really clean, simple build system, it can be pretty quick, but more complex build systems, which we often see in HPC applications, may take longer. And I do want to stress, HIP is designed to be a portable layer. It's designed to both be on top of ROCm and CUDA. So as you do a port, you should be considering taking advantage of that, keep that portability, because it can really pay off in the long run. You end up with a single source code to maintain. You may have a few things you have to have separate routines for CUDA and ROCm, but they should be minimized so that maintenance is much easier. And I do want to stress portability and open source are core values for AMD. We really do want to stress that. And I know, as being an application developer myself, these are really key things for large applications. So Hippify Perl is in the ROCm directory, in the bin directory. It has been Hippify Perl.sh or Hippify Perl without the .sh, so depending on the version of ROCm that you have. And you run that tool. The argument is the CUDA code, and you can redirect the output to a CPP file that you can compile with your standard HIP compiler. And so we see HipCC, that resulting file. You may need the architecture you're compiling to. HipCC does do an auto detect of the GPU type, but sometimes that is not a reliable thing, or you may be compiling on the front end. So you may need to add the argument to tell it which GPU you're compiling for. So in practice, you would Hippify your source code, check it back into version control, and then try to build it and work on the issues that result during that process. Generally, the manual work is fairly small. It does take some effort to validate the code at this point. You can convert to ROCm code. So there is a ROCm ROC option to a HIPAA Perl. It's not something I would recommend in general, but it may be something valuable for some projects. So here's the help page for HIPAA Perl, and there's a lot of different options: an in-place option, a stats option. You know, you can also tell it to use the CUDA kernel launch syntax or the HIP launch kernel function call, and people have different preferences with that. So there is an option to override and use the interface that you prefer for launching a kernel. So HIPAA Clang, you build this from source, and you can run the unit test just to make sure that it's built correctly. You do need a CUDA installation, the headers, because it needs to check the headers as part of the process. And so, and you may need to point to where those headers are located. And to read about the different HIPAA tools, both HIPAA Perl and HIPAA Clang, you can go to this ROCm developer tool site. So, you know, these are not perfect tools. They're not really running your application, checking correctness, comparing between CUDA and ROCm. They're just doing a string replacement in general. Some of the things that will trip you up are if you have hard-coded the warp size into your code. You may need to search for 32 and see if you need to convert it to 64 for ROCm. And there's some functions that don't have a HIP version. So some of those will not translate. And that's because there is not a call to translate to. And this is somewhat the hardware differences or the small languages differences between ROCm and CUDA. You know, inline PTX assembly is just not going to be converted. So you have to do that manually. Most of the library calls do convert, but not all of them are handled. And so the hardest work here generally is converting your build system, whatever tools you use for that, whatever build system. So if you use CMake or AutoConf, you may have a fair amount of work to adapt it for HIP. And in particular, if you want to maintain portability and either compile for CUDA or ROCm, that may take some additional work as well. So what should you keep your eye out for in the porting process? Well, we mentioned the PTX assembly, some of the CUDA intrinsics. Here we're recommending just search for 32 in your CUDA code. And there are a couple tools that allow you to portably handle warp size. So you can use a pound define warp size or this props warp size. Now, most of the AMD hardware does run with 64 for the wavefront size, but there are some of the commodity GPUs that have a smaller warp size. So you may want to also look at some of the optimization for performance, things like minimizing register usage may be different for NVIDIA and AMD hardware. And there still are some unsupported functions. Not everything has been ported from CUDA to HIP. The functions that have been ported in the libraries are the most commonly used functions. by the key applications that AMD has ported to run on the AMD GPUs, but not everything is ported over. If you do have an issue with an unsupported function, that is something that you can contact us about. So with Fortran, there's not as easy a process to convert the code, the CUDA code to use HIP. So you can, if there's no CUDA code in the Fortran, then you can just HIPify the CUDA part and then compile and link. If you're using CUDA Fortran, you can call those HIP functions using HipFort. And so we talked about that in our earlier talk. So we basically wrap all the C functions in Fortran, and we call them using that ISO-C binding that we talked about. And there's one interface with Fortran 2003 and a different interface for HipFort using 2008. And so that's been used by quite a few projects if they're using Fortran. So what alternatives do we have to HIP? Well, we have higher level languages, and AMD supports the OpenMP standard, the 5.0 target offload. So there is an OpenMP compiler in the ROCm stack. There's also a AMD OpenMP compiler called AOMP that has some more recent experimental stuff that you can try. And then GCC has some OpenMP offload support. And that's being improved quite rapidly. And it still doesn't support MI200s. It only supports up through MI100 at this point, but it will not be long before it supports the MI200 series. And GCC also offers the OpenACC language. So that's another porting path that you can use depending on what your application development has utilized so far. There's a tool which will convert OpenACC code to OpenMP, the CLAC tool from Oak Ridge. There's also one from Intel that has just recently been released. And LLVM has said that they will support the OpenACC through a translation from OpenACC to OpenMP and then compile it. I'm not sure quite the status of that at this current point. So, we have several different avenues for OpenMP through ROCm, through this advanced OpenMP compiler, the research compiler. We also have HPE compilers. So you're on Lumi. The HPE compilers are quite mature. They've been around for quite a while. So those are usually the ones that most people are using on the Lumi if they're using OpenMP or OpenACC. And I do want to make a note, though, that the HPC, the HPE compiler for C and C++ has been moved over to LLVM, so it no longer supports OpenACC. The Fortran compiler still does. And you can mix the OpenMP and OpenACC if you want with that compiler. So the GNU compilers, where do they stand? Well, GCC 13 will support MI200. It's supposed to be released pretty soon, and it supports both OpenMP and OpenACC. Now, the performance of these compilers is still a work in progress. They're really working hard at supporting all the syntax for these for the OpenMP language. So what are your, when you're trying to program for the AMD GPUs, you need to know a little bit about what the hardware looks like. And so we talked earlier about the AMD hardware, but these are some things you want to keep in mind. There's 110 compute units. What does that mean to you? There's a lot of different processing cores on a GPU. You often have to get to thousands of individual work tasks to keep a GPU busy. So number one job for programmers is to expose all the parallelism they can. You also need to keep in mind the wavefront size of 64, and then you have 4 SIMD units per CU. So in OpenMP, you can specify this in the Pragma options, the number of teams, your thread limit, and customize it for the hardware. Okay, so that's the end of that talk. So do we have any questions on that? Okay, we're about 5 minutes behind schedule, so I'm going to go ahead and go over to the exercises. Again, we're going to use that HackMD document. Okay, are you able to see the HackMD now? Okay.
It's small.
Okay, so in the HIPify section of the HackMD, we start out with some of the examples again under HPC training examples, and it's under the HIPify subdirectory. And there's a mini n-body code that comes from some ports from GPU gems from some years ago, and there's a CUDA port of that mini n-body. So we're going to take that, and there's several versions of it. It really doesn't matter which one you pick. So there's a mini n-body, CUDA n-body dash original.cu. So that's one you could try converting. And you can go in there and by hand go and search for all the CUDA keywords and then manually convert that code to HIP. And then you compile it with HIPCC. If you do that process, it gives you an idea what the HIPify tools need to do. The second exercise, we're going to use the HIPify tools to do that conversion. So in this example, we use HIPify Perl in place print stats on that code. And so if we do that for the n-body original.cu code, we're going to get some output telling us what it, what calls it's going to convert, how many of them are there, and it will tell you if there's some that it can't convert. Now we can do that conversion, create a .cpp file, and then use the HIP to compile that program. So there's a couple issues in that original CUDA code. There's some printouts that don't convert easily. And so there's a -D SHMOO that will skip those lines of code. And if you do this HIPCC of the n-body orig.cu, which has been converted, or if you rename it to CPP, then you can create your executable. You may need to add the offload architecture flag to that HIPCC command. And so you're going to follow the same process of getting yourself an allocation using the salloc command that we used in the earlier examples. Then you're going to do this conversion. You will have to load the same modules. So I'm just going to scan back up, and so we still need to do this salloc and the module loads. Once we have done that, we can use the Hipify Perl script and do the conversion. Then we can compile it. And to run it, you got to use srun to put it back on the compute node and run the n-body orig executable. So it's a fairly simple process to do the conversion for simple codes. For larger codes, you may run into problems, especially if you've done anything tricky with the CUDA code. But it's still a fairly simple process to do the conversion. Now, at the end of the HackMD is a short section for HipFort on how to install HipFort and then test it. If you need to use HipFort, it's a pretty quick process. It doesn't take long to compile those wrappers. So with that, I think we've covered all of our all the stuff about HIP, which is what today was for. So I just want to summarize where we're at. I see George has gotten back, so we will summarize where we're at after the first day. So with the first day's talks, you should have gotten an idea of the HIP language, how similar it is to CUDA, the advantages of HIP being that, first of all, that you can run on AMD hardware, but second of all, that you now have portable code, that we have tools that will help that conversion, and that there are ways to access the HIP routines from Fortran. So many applications have been ported using these tools fairly quickly. Tomorrow we'll go into other languages, but understanding HIP is kind of essential, even if you're going to program in another language. Understanding the HIP calls gives you an understanding of what the GPU is doing. So it's beneficial even if you're using a higher level language. With that, I'm going to open up for questions. Is anybody confused on any part of HIP and how it works? Okay, again, sometimes the hardest part of these workshops is getting onto the system. If you didn't get on at the beginning of this session, I do encourage you to walk through some of these examples, use that HackMD, and try it out yourself. You really only learn this well by actually doing hands-on exercises. And I do have a comment. It'd be good to walk through the exercises together. I think we don't have enough time to do that, but I will see.
Hi, Bob. I had a general question about the offloading itself.
Right.
So just wondering as to how much overhead compared to having actual kernel, CUDA kernel, how much overhead does the offloading itself bring in? I mean, do you have any idea about, or has it been measured?
So I'm not quite sure what you're asking, but I will answer both. I will answer, give you a more general answer. So what is the overhead of HIP versus CUDA or ROCm? It's very low overhead. It's basically, it is going to just do enter the HIP routine, switch over to the CUDA routine and execute it. So the overhead is very low. I'm not going to say zero, but it's very, very low. So generally people find the performance is the same using HIP as using CUDA directly or ROCm directly.
Oh, no. My question was regarding the OpenMP offloading. So
that was the second thing I was going to answer. So OpenMP offloading, the overhead can vary quite a bit. It depends a lot on your application. It depends on the compiler. We have seen where you get almost equivalent performance. We have also seen where it's where there is quite a bit of inefficiencies. Sometimes you can fix those inefficiencies through working on the program a little bit more. So it varies depending on your application. There are some things that are easier to access through the HIP code. My recommendation here is program at the higher level. Your productivity is much, much better. And if you find that there is one routine that you're not getting the performance you would like, then convert that one to HIP and use it. Use both HIP and OpenMP in your application. So you can mix them. But maintaining an OpenMP code is much easier than a HIP code. So, and that depends a lot on your application and what you're trying to do. Does that answer your question?
Yeah, it does. Thank you.
Yeah. I think also the other thing that people are concerned about with languages such as OpenMP and OpenACC is portability. We talked about portability with HIP. OpenMP and OpenACC are on paper very portable, and in the long term are going to be very portable. But compilers are catching up. There's a lot of work the compiler developers need to do to support those languages and all the other challenges of HPC applications. And so, they're playing a catch-up game. One of the things you really want to be able to do is to, let's say, run OpenMP on your laptop, do code development, then move to the HPC systems and run it there for performance. And So looking at what your options are for that can be, you should spend a little bit of time thinking about that. The compilers are getting are improving rapidly, and we should have more portability in the near future. Performance may not be optimal with all of them. It's going to take a little longer for them to catch up on making everything perform well. Okay, I hope I answered that question.
Yep.
Are there any? Okay, good. Are there any other questions? Okay, so I'm going to wrap up here. If you have more questions as you're working through the exercises on your own time, the system is available to you through the full duration of the workshop. You can test it as you have time. If you have questions, you can email me directly or check with us when we meet tomorrow. Tomorrow, we're going to try to give you an overview of all the different options you have for programming or developing an application for AMD GPUs. Just give you a high-level view of all the languages. And we can't cover all of them, but we're going to hit the key ones, the most common ones. I do encourage you to try all the different languages. Even if you think you have a favorite right now, it is good to know what the other options are out there. And then we're going to be getting into the how to optimize things and the tools that are available on Thursday and Friday. Okay, I think with that, I'm going to go ahead and conclude.